All right. Okay, so this is a pretty fun lecture, although it's a little bit different. So we're moving to a new set of topics as we enter the last part of class. I think next week we might go back and maybe do some fun topics related to what we did last week. But I want to get some of this stuff in um, now while we can still do a little bit of homework and get some practice at some of the topics this week. So, right, so what are we doing this week? So this week we'll do something that's a little bit different in perspective than what we've done all semester, because in some sense we'll be doing a sort of average analysis of algorithms. Okay, and we'll do it in two different ways. One is this thing called amortized analysis, which often comes up when analyzing data structures, although it also comes up in other situations. And this is about operations that don't always take a certain amount of time. Some may be big, some might be small, and stuff like that. But if you do like 100 of these operations, in hindsight, you'll see that on average, maybe it was smaller than the worst case. We'll do that today, and that will be the main topic. And on Thursday, we'll do a little bit of introducing randomized algorithms. Okay, and there the algorithms will not always do the same thing every time. It'll flip a coin and decide to go left or go right and make various choices. And there we'll sort of average over, try to analyze the running time on average, where the average is over all those coins it flips. Imagine like flipping one set of coins and running the algorithm, that's one running time. And with the same input, suppose you had flipped another set of coins and you got a different running time, and so on and so forth. Imagine doing this experiment ad infimum. What is the average? So one thing, maybe there's two aspects of this which is what I really like. One is that everything this week is actually quite practical. So some of the data structures we'll discuss today are like really simple and are the ones that are actually often used. And because we relax the analysis to go from like really strict worst case to this amortized analysis, sometimes that wiggle room lets you do a simpler algorithm and one that's actually more practical in practice. Same with randomized algorithms. So actually allowing for flipping coins and stuff can often lead to much simpler algorithms. A famous example is quick select, which is often or quick sort. And the analysis is a little bit trickier because it becomes a little bit more numerical, right? Because you have to analyze some kind of probabilistic experiment. But the code, the algorithm itself, is like dead simple, and so that's a really good trade-off in practice. Another thing binding these two things is that although we're analyzing the algorithms on average in some sense of the word, we're still going to retain all of the same sort of worst case robustness. So everything we'll do today is we'll kind of analyze things on average or in the aggregate, but in the worst case against the worst possible input. So like you could still choose the worst possible input, and no matter the input, it'll still on average look pretty good. Same with the randomized algorithms. You could give me a terrible, terrible input. No matter the input, on average, it'll still look pretty good. Okay, so we're not saying like, oh, we'll do random inputs and on average, how does it do? No, we're going to still do algorithms that still have good performance guarantees no matter the input. So you still have strong worst case guarantees. It's just that when we're declaring the running time or something like that, it'll be slightly different because of the introduction of the word average. All right, so we'll make that more concrete. Okay, but I think these are both kind of, it's a very interesting concept and sort of a nice expanded way of looking at algorithms. All right, so today we're doing amortized analysis. And so I'll start with the simplest example and something you guys are all used to, almost going back to the first lecture, just binary counters, right? So suppose I have an integer I and I call I plus plus, right? We all know what that does. It takes I, increases it by 1, and saves it in the register. Okay, no big deal. So what's that doing in bits? So you start at like 0, and you flip one bit to 1, and then you go to like 0, 1, and then you'll go to 1, 1, and then you'll go to, I guess, from your point of view, 0, 0, 1 or something. But you keep flipping bits, right? And it kind of keeps rotating through. And obviously that's a pretty simple thing. And you've probably never thought about the running time of this operation, right? You're just flipping like a bit or something. So is this in fact a constant time operation? Yeah, so I see some heads shaking no. So when does this become slower? Yeah. Yeah, so the more ones you get, a long string of ones, and I add one, now I have to flip a ton of bits to zero. Obviously, in a computer, if it's just 32 bits and it's kind of sped up by hardware, it's not a big deal. But we're doing theory here, so in principle, this could be really, really long, and it's not technically a constant time operation anymore. Of course, you've never ever worried about this ever, and you've probably incremented integers many times and have never had any issue with it, right? And so we are going to argue that it's still nonetheless a pretty good operation, even though it's not technically a worst case no matter what constant time operation. But I still want to argue that its running time is very reliable. Okay. And so to do that, we're going to zoom out a little bit and not just worry about one increment at a time, but say, okay, if I did 1,000,000 increments, what's the total time spent on the 1,000,000 increments? If I did 10 billion increments, what's the total time spent on 10 billion increments? And so on and so forth. Okay, if I want to argue that maybe on average, I'm still flipping just like 1 or 2 bits, right? That incrementing 10 billion times maybe flips 20 billion bits total. So that on average, it looks like I'm flipping just 2 at a time, even though, the first few are really fast, and every once in a while, there's a slow one that flips a lot of bits. Okay, so that's the question. We're going to reframe the question a little bit differently. Instead of just asking what's the worst case over any individual operation, I'm instead going to ask, as I go from 1 to n for some arbitrary n, what's the total number of bits I flip? Because that's almost what you observe in practice, right? Because you are just going to run the code, and you're not going to sit there like measuring every single increment. You're going to just see what the running time was in the aggregate. Okay. But there's a little flexibility there, right? It's a more relaxed question. Of course, if you had a really good worst case, I could just do worst case times n and get a running time. But here I don't have a great worst case. The worst case times n wouldn't be very good here. All right, so this question. As I go from 1 to n, how many total flips do I make? All right, so let's imagine just all the bits, the first bit, the least significant bit, the second bit, the third bit, onto the kth. All right, how often does the first bit flip? Yeah, okay. Okay, every single time for a total of n. Okay, of course, every time, right? The 1 digits, okay. What about the second bit? How often does that flip? Half the time. So in total, how many times as I go from 1 to n? N by 2. I guess technically n by 2 rounded down. All right. Now let's look at the third least significant bit. How often does that flip? I just see nodding like it's obvious. Someone just say it. Say it proudly. Okay, 4. I think I heard 4. Every 4 times, and you do n over 4 times, right? So I think you guys see the pattern. What happens on the kth bit? How often does the kth bit, like the 100th bit? How often does the kth bit flip? Every 2 to the k times. Oh, I guess cap minus 1. And so the number of times it flips is like n over 2 to the k minus 1. Okay? And we can keep going. If I add all this up, right, and in particular, I'm looking at the total number of flips. What's the total number of flips? 2n, at most 2n, right? Because you're going to get n plus n over 2 plus n over 4 plus n over 8, 1 plus 1 half plus 1 over 1/8, that all adds up to 2. Okay? So in the aggregate, I'll only flip 2n times. So in hindsight, It's as if I was flipping 2 bits every time, even though I'm not actually flipping 2 bits every time. So probably what you always thought of it being a constant time operation is mildly justified. Unless you're actually measuring each operation individually, you wouldn't be able to distinguish between an actual worst case of 2 and this average, in hindsight, running time of 2 bits. Okay, so this is called amortized time. Okay, so right now we have something where, n increments leads to 2n bit flips, or 2n time, big O n time. And so each increment will take constant time on average in hindsight. Okay, on average in hindsight. And that's what we call amortized time. Okay, so when I say something has constant amortized time, that means if I ran it 1 billion times, each individual operation may take more or less than constant time. Probably not less, but some may be more expensive here and there. But in the aggregate, it should still take like big O of 1 billion time. So, right. So when we say something has t amortized time, some operation has t amortized time for some value t, that means if I ran it n times, it should take big O of nt time. Yeah. Well, before we were only analyzing the operation of incrementing. So we didn't do addition. Just increasing by 1, increasing by 1, increasing by 1. And this is the simplest example I could think of to get us going to help demonstrate the concept. We'll have more like interesting data structures and stuff coming up. So in the binary counter, there's only one operation, but we're going to have data structures that have, 3 or 4 different insert, delete, lookup, maybe a handful of different operations. And I might say, this operation takes constant amortized time, and this operation takes log n amortized time, and this operation takes log n squared amortized time. So what that means is like if I ran the first operation 10 times and the second operation 20 times, the total running time should look like 10 times a constant plus 20 times a constant, and so on and so forth. Even though, again, each individual operation may be more or less than its stated amortized time, but you should still be able to add it up in the aggregate. Yeah, question? Okay. All right, so that's how we define amortized analysis. All right, how do you do amortized analysis? So one is, at the end of the day, you just want to add them all up. So like a direct analysis like we just did is fine. Okay. But as we do more complicated things, it might be hard to see how to analyze things directly. So we'll go over 2 different alternative approaches, which are really more like kind of heuristics to help you get the amortized bounds. One is sort of based on creating credits. It's like we'll do some concrete example. Actually, we'll go through both of these with the binary counter in a moment. One is called credit schemes, or sometimes called the banker's method. The idea is you kind of pay credits that can be exchanged in for work later. And the other is called the potential function method, and that's sort of like inspired by physics, where you have some potential function that's sort of like maybe it's going up and up and up and up, and then whenever you have to do a really expensive operation, maybe the potential goes down and it kind of pays for the effort to do something expensive. But I'll explain with an example. And these aren't like super formal things. They're just different ways to help you get an amortized analysis. All right, so let me explain these credit schemes. Okay, so the high level idea, every once in a while, let's take the binary counter example. Every once in a while, one of those operations gets way more expensive than the average, right? Like I have a bunch of ones and I have to flip them all to 0. So the idea is that as you're doing the easy ones, like at the beginning, there's very few very few bits being flipped. I'm going to sort of imagine paying an extra $1 that can be charged in for like constant work later. So I'm hoping that by the time I get to the point where I need to flip 100 bits, I've already saved $100 in the bank that I can use to pay for flipping those bits. Okay. And so, uh, right, right. Okay, so let's see this. All right, so we're going to try to come up with a credit scheme, okay, to help justify those cases when I have to flip, lots of bits and stuff like that. Okay, so I'm again looking at binary counters. I'm just incrementing. Okay, so all right. So here's how I've sort of structured it. I've left some space for you guys to fill in. All right, so when I increase something, I'm going to buy a bunch of credits to pay for operations later. And I'm going to imagine actually placing the credits on various bits so that it can be used to flip the bit later. Okay, so, and they could be fractional amounts. So let's see. Maybe I'll get us started. So I imagine like putting one credit on the first bit. So I just put $1 on the first bit, and that first bit's going to get flipped and it's going to use the dollar right away. Okay. Now, how many dollars would I need to put on the second bit to make sure that I've accrued $1 by the time it flips? A half. Okay. So if I imagine putting 50 cents on the second bit, right? Then every two iterations I'll have $1, and every two iteration that bit flips. So every time the bit flips, I'll have already saved $1, and I can pay for that work. All right, then continuing on, how much credit should I put on the third bit? All right, 1/4, 25 cents, right? So every four iterations, the third bit will have $1. And every four iterations, the third bit will flip over. So every time I flip the bit, I have $1 there to spend. Okay. And in general, the ith bit is going to have, I should give it how many credits? Yeah, something like 1/2 to the I minus 1. Okay. All right. And so if I do this, then every time the 1 millionth bit flips, it should have $1 there ready to pay for the bit flip. So what I'm doing is, later on, there's some work coming up in the future, right? So when I increase just by one, that bit later on is getting that much closer to flipping. It's gradually getting a little closer to eventually flipping. So we're paying for that work ahead of time. Okay. All right, so each iteration, how much total credits do we pay? Okay, just two. Plus, we also do some constant work. So I do some constant work and I pay 2 credits, and those 2 credits will I'm just saving up work, so to speak. I'm paying now for the work I'll do later to flip, all these bits. Okay. So that's the idea. Whenever I need to flip the ith bit, I'll already have 1 credit there to pay for it. Okay. So, all right. So that's the high level idea. We'll go through other examples and more practice. Okay. So the only rule. Okay. So at the end of the day, you get to devise the credit scheme, and maybe that wasn't the only way to come up with a nice credit scheme for the bit flipping, but it seemed natural to me. And at the end of the day, your amortized time is whatever's the best upper bound you can get on the true running time plus the change in credit. Okay, so in the case of the binary counter, um, first I'm going to pay 2 credits. So immediately the credits go up by 2. Okay, and the running time is proportional to the number of bits I flip. Okay, but every time I flip a bit, the number of credits goes down by 1. Okay, so the change in credit will offset the running time, and so I'll end up with a constant amortized time. Okay. All right. Very sensitive today. Okay. Um, right, and that's the rule. So what I decided to do this lecture is not to do. It's not hard to show that if as long as you follow these rules, you can like pull out a direct analysis and really formally show you get the right amortized running time. That's in the notes. It's only like a paragraph. It's not too long, but I wanted to focus more today on just how to use these things and the applications and why it's fun. So hopefully you guys will follow up at some point. Okay. All right. So that's credit schemes. Let me talk about the other approach, the potential method. So this is sort of like inspired by physics, right? Like it's like if you're really high off the ground, then you have some like potential energy from when you fall and you crash and you hurt yourself. Okay, so the idea is that we'll come up with some kind of potential function that sort of is based on the state of your, usually a data structure. So we'll have some kind of potential function that in some way reflects the state of, say, our binary counter. Okay? And the idea is that okay, so at the end of the day, our rule is going to be that the amortized cost is some upper bound on the actual time you spend plus the change in potential. And so we'll try to set up the potential so that hopefully whenever you're doing like a real expensive operation in real time, like you're flipping a lot of bits, the potential is also going down by a lot. Okay, okay. So, okay. All right, so right, okay. All right, so I guess I left it blank to give you guys a chance to guess. It's a little bit tricky to guess, but maybe just trying to think of one is still be a good learning experience. All right, so for a binary counter, I want to come up with a potential function to help justify or help kind of cancel out that expensive operation where I have a bunch of ones that all flip to zero. Right? Because most of the time I just flip like 1, 0 to 1. But every once in a while I have to flip a bunch of ones to zero. Okay? So I want to think of a potential function that somehow reflects the state of the binary counter so that if I'm flipping a bunch of ones to zero, the potential goes down by a lot and can pay for that work. I know it's hard to guess because you've never seen an example of it before. Oh, we can track the number of ones. That's actually what I had. All right. So I'll define phi, Greek phi, to be the number of bits that are currently set to 1. So like in a bad operation, I have 100 straight ones, right? And I increase and then 100 ones go down to 0. So I'm paying 100 running time. But the potential also will go down by 100. So uh, so each time I increase, if I do have to flip a bunch of ones back to 0, I have to flip like 100 ones back to 0, the potential will also go down by 100. So that decrease in potential will pay for the bits you flipped. Okay? And then you flip 1, 0 back to 1, and then so it just becomes constant time. So the potential will pay for all the ones that get flipped back to 0, and then you flip at most 1, 0 to 1, so you just pay 1. Or you pay 1 in running time and then 1 more in the potential function, so you pay 2, but whatever, you pay a constant. Okay. So a potential method, I don't know if it's the easiest to come up with, but often once you come up with, can look really slick in hindsight, right? Like, oh, just number of bits set to 1. And then it's very easy to verify. So sometimes you can get very slick arguments using a potential method. Okay. Is there anything down here? Okay. Yeah. All right. Okay, so that's the potential method, and those are the three kind of basic ways to do they're not the only ways to pull off an amortized analysis. At the end of the day, you need to kind of appeal to the direct approach, But if you're able to come up with a credit scheme or a potential function method and follow the rules, then there's sort of a generic way to convert that automatically to a direct analysis, and you don't have to do that because there's a theorem in the notes. Okay, so yeah. Isn't it already what? Yes. Okay. So let me actually highlight this. So, okay, I was being a little lazy. When I write delta phi, that means the change in potential. Uh, I don't know because it's shorter to write than change in potential. And uh, so imagine at the very beginning you have an empty binary counter set to zero. The potential is zero. The first iteration, one of the bits becomes one. The potential becomes one. And you also paid one in running time. So the amortized cost would be like one plus one is two. So it's bounded by a constant. The next iteration, that one goes to a zero, and then the next you flip a zero to a one. So your potential actually stays the same, and you did 2 units of work, you flipped 2 bits, so the cost again was two. The running time plus the change of potential was two. Now in the next iteration, you're at one, 0, and you flip one to become one. So you spent 1 unit of time, and your potential went up by one. So again, amortized cost is two. All right, now you finally have two ones. Okay, and that'll become like whatever 0, 0, 1. Right? The two ones that went down to zero, the potential went down by two, and it will pay for that. But then you put one back up, and so the potential went up by one, and then you have one more unit of work. So again, the cost was one. Now, if you have n ones or something like that, right? Then your potential is high, but that's okay. There's nothing wrong with the potential being high. It's just that it's going to pay. It's almost a good thing because you've sort of saved up a lot of potential work to be charged off later. So all you're really worried about is how much you're increasing the potential each step along the way, because that's what determines your amortized time. If you accrue a large potential over time, that's sort of like a lot of saved up work in a certain sense, and that's okay. That's sort of very healthy. Well, no. So okay. The question was, are we always doing the same amount of work? So if you have a bunch of ones, then you're gonna have to flip all of them. So that's a lot more work. If you don't have any ones, then you're not flipping. You're only flipping the initial zero to a one. Oh, well, maybe binary counters are such a simple example that it's not super convincing yet why we should, use this method compared to the other ones. I mean, the direct analysis was probably simple enough for this. But maybe when we get into more hairy data structures with more than one operations and one funky stuff going along, you may or may not find this convenient. So it's all just a matter of taste. But some people like this approach. Okay. And at some level, you can even think of the credit scheme as a potential method where the number of credits is the potential and stuff like that. But okay, anyway, not too formal. All right, so those are three different approaches. And now I thought we'd kind of go through some examples and get some practice. Okay. All right, so I'm sure you guys have all used, I don't know, does anyone program in Java anymore? On the old days, like 10 years ago, there was this language called Java. And so one ubiquitous data structure is called the array list. It's an array backed list. Okay. So the idea is kind of really simple. Or what's great about an array, right? If you have all the elements in the array, you can access any one of them in constant time. Okay. But what's the main problem with having all your elements in an array? If you want to add another element and you're out of space, you're screwed, right? So, just using an array to implement a list is tricky because you want to try to guess how much capacity you need ahead of time. And the whole point of data structures is you don't want to anticipate your needs ahead of time. You want it to kind of dynamically adapt and stuff like that, right? Nonetheless, the main data structure for lists in Java is based on arrays. So the question is, how do they do it? All right, so that's maybe a question for you guys. Suppose I wanted to use arrays to implement lists, right? So I want to allocate a lot of space and gradually fill them up with elements, right? But my main issue is that I want, my total space to be pretty close to the actual size of the list. I don't want to allocate 1 billion slots and only fill up 2, right? And I don't want to allocate something small and find out that, I have to make a bigger array, right? All right, so any ideas about how to remedy this? Any tricks? Yeah. Okay, how much more? Okay, so let's say I've just filled up my array and I want one more slot. How much would you increase by? Sorry, I'm so congested. Yeah. Okay, a ratio. Like, give me an example. Okay, so increase by 50%. Okay. Yeah, we could do that. I'm going to be even lazier. I'm just going to double it every time. Okay, maybe actual implementations are more shrewd, but I don't care. Okay, so if I've already got n slots allocated, I want to put an n plus 1. I'm just going to allocate an array of size 2n, copy n elements over, okay, and then put the n plus 1th item in that slot, and now it's still like basically half empty, but it's okay, it's a constant factor. Okay, so that is what the Java array list does, and analogous things in C++ and so forth. Okay, so obviously this is not a constant time operation, right? So it took n time because I had to allocate something of size 2n and I had to copy n elements over. Okay. But this is still a very good data structure in practice. People use this all the time. It's really good. But it's not constant worst case time. So how can I justify this very, cute approach? Yes. Yes, exactly. Okay, so we're going to do amortized analysis. So the suggestion was we roughly only have to do big O of n work every n. Okay, so we're going to try to argue that the array list will let you do, well, you could do lookup in constant time, right? Because it's an array, so you can go directly to the index. But it'll also let you do append in constant amortized time. And probably a homework problem will be figuring out how to do deletion from the end in constant amortized time as well. Okay, but we'll just focus on append together. All right. So how? Right. So I want to argue that n appends should take big O of n time because that would be constant time per append. Okay. And now you guys have 3 different possible ways to try to do this. You can do a direct analysis. You can do a credit scheme. You can try to do a potential method. You can pick any one you want. I'm going to give you guys a chance to try to think of a way to argue that appending takes constant amortized time. Yeah. All right, credit scheme. How might I come up with a credit scheme for this? Okay, so let's say that okay, so each append will save 1 extra credit. Okay? And then I guess the idea is that the credits will pay for doubling, right? Okay, that means okay. So once I get to like n elements, right, and I double to 2n, it'll take roughly n or 2n work. So I need to make sure I have something on the order of n credits. How can I argue that I have roughly n credits by the time I get to n? Yeah. Yeah, well, but you have to be a little bit careful. Okay, so that makes sense. Okay, we've gotten to n, so haven't we saved up n credits, right, before we double? So the only thing to keep track of is that, let's say I go like 1, 2, and I save up 2 credits, and it doubles, right, from 2 to 4. So I spent those 2 credits from when those first two got inserted, right? So even though we got to n, we have to imagine you start at like 1, an array of size 1. And so over time, each time it doubles, we're roughly spending all our credits. So you don't necessarily have all n credits because some of those have already been spent. Yeah. Ah, okay. Yeah, so we're otherwise very close to the truth. Unfortunately, I didn't choose n to be a power of 2. But roughly, if this was kind of like n over 2, okay, it's not quite, right? We have n over 2 new elements since the last time we doubled, right? Because we doubled from n over 2 to n, and now we're going to go from n to 2n. But since the last time I doubled, we did get n over 2 credits. So I do have n over 2 credits in the bank by the time I get to n. And okay, so we'll just have each credit count as 4 units of work instead of 2 units of work, and that's totally fine. Okay, the point is that we have something proportional to n credits in the bank. Okay, so those n over 2 credits will pay for the big O of n work. Okay, so since the last time I doubled, at least half of those elements are new, and those are the ones that give me the credits I need to pay for the next double. Okay, this is why it actually needs to be any constant factor bigger would have been fine, but it needs to be a constant factor bigger to pull off this argument. Okay. All right. Okay, so that's n over 2 depends. This is done a little bit more slowly and formally in the notes. Since the last, and in better handwriting, doubling, and that, pays for it. All right, okay. That's good enough. So that's a credit scheme. I don't know if anyone wants to venture and do a potential function or anything like that. I think I give all the examples in the notes, but okay, we'll keep going. I left a lot of blank space. Okay. All right, any questions though about the doubling trick? It's obviously a very practical thing. You can use this for heaps. You can use this for all sorts of things. All right. So the homework will ask you how to do inserting and deleting. All right. Okay. Next application is going to be search trees. I'm sure you guys did this in your data structures class once before. So I'll just go over the basics. So simple binary search trees. Okay, so you have a bunch of keys, which I guess in this example, I'm letting them be numbers. But in general, it's just anything comparable. It could be a bunch of strings and they're sorted in alphabetical order. Okay. And the idea is really simple. Each node corresponds to a key, a name, or whatever. Okay. And in the left subtree, I'll have all the keys that are smaller. Is that your left? Yeah. And in the right subtree, you have everything that's bigger. So if I'm looking for the number 100, and this is like 5, I go to the right, and I go left. I can navigate my way through the tree going left or right, depending on whether it's bigger or smaller. And eventually I'll find the key I'm looking for, or I'll get to the bottom and realize it's not in the tree. Okay, so it's a simple way to organize, simple data structure. Okay, left, right, left, right. Okay. All right, so when you have all your elements, your keys in a tree, you can ask questions like, is a key in the tree, right? Um, or you could say, oh, here's some key. What's the first key that's bigger than it? Or you could say, what are all the keys between A and Z, right? Or how many keys are between A and Z? There's lots of like different games you can play once things are in the tree. So for example, if you want to ask a question like, does this tree contain the number 7? You would search through, and in that example, you would conclude it's not there. A more elaborate thing like, can you list all the keys between 7 and 18, right? What you can kind of do is you can search through the tree and figure out where 7 and 18 would be, right? And then you just have to list off all the keys kind of in order that are sort of between these boundaries. Okay? So by the time you have things in a tree, then it actually becomes very easy to list off a whole range of keys. Other simple things. All right. How many keys are between, 5 and 25 here? Now, we could do something like we just did where, if I can list off all the keys, then I can just go through and count them, right? But that's kind of slow because you have to enumerate everything. One trick you can do is for every subtree, you can write down the number of elements in that subtree. So in lime green, you'll see like there's that subtree that's looks like a triangle, and I wrote 3 at the top because there's 3 nodes in that subtree. Okay. Now when I want to do this range counting operation, as it's called, so there's sort of 2 paths, right, to go to the ends of that range, and there's a bunch of like trees hanging off in the middle. And those trees, instead of going through all of them and counting them all up, I can just add up the total, 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 add up the total. So at the end of the day, I just have to kind of trace the paths to the ends of the range and just add up the inner trees. Okay? So the running time is kind of proportional to the length of these paths. What's going on? All right, I don't know why I'm having so much trouble. Okay, that's not very good. Okay, okay, what was the point of this? Oh, okay, the point is that in all those examples, the running time of an operation is proportional to really how long that path is to the bottom, which in the worst case is the height of the tree. Okay, so all these, you get all these data structures, where the goal is to try to make your tree look like the left instead of the right. Okay, so ideally we want to get balanced search trees so that all these operations that go from top to bottom are relatively fast. The worst case is something like on the right, where all the nodes are just in a line. You have to go all the way down, and it takes time n to search n keys. Okay. Now, if you had all the keys ahead of time, it's not so hard to make something that looks like something on the left, right? So if I gave you a big list, and they say, oh, make a balanced binary search tree, what would you do? Well, one approach is to find you want your root to be the median, right? Because that'll split things in half. Okay, find the median, and then recurse on both sides. Half the input builds a tree, half the input builds a tree. N plus 2 tn over 2, you'll get n log n. You can also sort the elements all ahead of time, And then you can just kind of pluck out the median and keep reusing the sorted parts. Okay, so it's not hard to do that. Okay, so all right. What's interesting though is what happens when you're inserting keys on the fly. Okay, so yeah, if you had all the keys ahead of time, you can build a perfect tree. That's fine. But what's more challenging is what happens if the keys are getting inserted online. So the most natural, easiest way to insert keys is to just search through the tree to where the key would be and then put it there. So just search until you get to that leaf where it would be and then put the key there. Okay? And then this way you'll maintain all the left, right, invariants and that'll be okay. But there's only one kind of issue. Why might this be bad? Sorry? Yeah, so if I did something like, as simple as inserting a bunch of keys in order, starting from 1, 2, 3, right? I put in 1, then I put in 2, and I put in 3, 4, 5, 6, 7, and I get this terribly unbalanced tree on like a very realistic insertion sequence. Maybe you are actually just inserting keys already sorted in order. Okay, so there's all these like really clever data structures that I'm sure some of you guys might have studied. Did you guys ever do AVL trees? You guys do like red-black trees? Okay. All I remember is that they were very subtle, and that's it. But they are actually able to maintain a balanced tree with log and height by various tricks to keep track of. Huh? On rotations and stuff like that. Um, okay, and yeah, I mean, all you need to know from your past classes is that that was relatively complicated. And so my goal today is to show you something that's much, much simpler. Okay, we're going to be very lazy. All right. Okay, so how do I keep, what's the laziest way to keep a tree balanced is roughly, uh, every time I notice that it's very unbalanced, I'll rebalance it. That's going to be the main approach. So what are we going to do technically? So we're going to do just a regular binary search tree, inserting keys at the bottom and stuff like that, nothing clever. But as I do, I'll keep track of the number of nodes in each subtree. So there you see annotated in green how many nodes are in the subtree. Okay. And so what these tallies let me do is they'll let me notice if one subtree has way more nodes than the other. If like one subtree has twice as many nodes as the other. Okay. And if that happens where one subtree is way bigger than the other, then I'm just going to optimally rebuild that entire tree. Okay. So that's the idea. If I detect a really big imbalance, like one subtree has twice as many nodes as the other, then I'm just going to rebuild the entire subtree optimally. Okay. One thing kind of nice is you can actually do this in linear time because those elements are already sorted for you. They're already in sorted order. You can just dump them into an array in sorted order. You don't have to sort them. That just takes linear time to dump them. And then you can just pluck out the median, pluck out the median, pluck out the median from your already sorted list and put a balanced tree back together in linear time. Okay, so rebalancing will take linear time and the total number of nodes at play. Okay. But the point is that this data structure is very simple, especially like inserting. I'm just inserting at the bottom. And along the way, I'll update my tallies, double check to see if anything gets too lopsided. And if nothing's lopsided, then I'm fine. If something gets lopsided, okay, I'll do some rebuilding and I'll fix it. Okay, but this is like, to me, simpler than, rotations and these red-black markings and stuff like that. Okay. All right, so, okay. First lemma. Okay, let's do this first lemma. The lemma, the claim, is that if I'm doing lazy, if I'm always kind of balancing the trees whenever they're too lopsided, the height is at most log n. So why is that height at most log n? As long as I'm making sure that any two subtrees are like within a factor of 2 of each other. So the claim is that as long as I implement this simple rule, the height is at most log n. Okay, so why? Yeah. Yeah, so let's say like in the bad case here, I go to the big subtree, right? Which is at most twice as big as the other one. So I am getting rid of roughly 1/3 of the nodes every time I go down. Okay, so the log base 3 over 2 of n, because it's going down by a factor of 2/3 every time, is still log n. Okay? All right, so we are always removing a constant factor whenever I go down one level in the tree, so I get a log n. Right. Yeah, it doesn't need to be 2. So any constant is only going to change the whole thing by a constant factor. So if it wasn't 3/2, if it was something more narrow like 11/10 or 101 divided by 100, is still be big O log n. Okay. All right, so that explains the rule, why it's useful. It keeps the height low. So now we just need to argue that insertion takes log n amortized time. Okay, so insertion, I'm just going to go down to the bottom of the tree and put the key there, and I'll update some of the tallies. And if along the way I find that some tree is unbalanced, I'll rebuild the whole thing. All right, so I'm leaving this to you guys. How can I argue that insertion takes log n amortized time? Yeah. Okay, so um okay. Um okay, so first I think first you said one thing good. It's always like a good way to get started, like, from a blank slate. The first sentence was, well, if we don't do any rebalancing, then you said it takes constant time. That's not quite true, but first that's a good idea, right? Like, oh, what if like nothing bad happens? Let's first sort that out, right? You do have to go through the tree that has height log n. So you actually spend log n time. Um, you spend log n time uh, just to insert the key, okay? And then comes the rebalancing and stuff like that. So uh, okay, so so the argument was if I have to rebalance, then probably one of the trees have to have like grown a lot, right? So if I look at like this example here, once upon a time, this used to also have 50, or they used to both be small, and over time it must have grown to be bigger. Maybe they both had less. Maybe once upon a time they both had, I don't know, 30. And the left and right both grew a little bit, but eventually the less one grew a lot more until it became twice as big. Okay? So at the very least, uh, the total size must have grown by at least 50% because one of the two sides must have doubled since the last rebalancing. Okay, so if I have to rebalance one particular node in a tree, then I must have doubled the size. Okay, all right, so that's definitely the intuition. Now I just want to get it down on paper. So if I can come up with some kind of potential function or credit scheme, right, just so we can write it down. So I think that's the idea. That's absolutely the idea. Now I just want to kind of crystallize it and formalize it and articulate this on paper. So how can I express this in the form of like a credit scheme or a potential function to really tie it all together? Let me know if the question doesn't make sense. I mean, what we're doing today is kind of brand new, I think, for everyone. So, okay. Okay, so let me just get you set up. So let's say that the root of this subtree is, I don't know, x. Okay. And then we'll make a potential just for this subtree. Okay, so I'll call it 5x is equal to something. And then later I'll have the total phi is maybe the sum over all the nodes 5x. Okay, so your idea was to have one potential function for each tree and the total potential will be all those potential functions added up. All right, so what would be a good potential function for this tree? So ideally, you want to set the potential function so that when you do rebalance, the potential goes down, and that'll pay for the effort to rebalance. Okay, difference. So this could be like absolute value of like the number in the left minus the number in the right, something like that, right? So if this gets really big, right? So if one is twice as big as the other, right? Then that potential function should be like at least n over 3, where n is the total number of nodes down there. So then when you rebalance, that potential will go from n over 3 to like 0 or 1. So you'll get back n over 3 points. And the n over 3 points can pay for the n time you need to rebalance the tree. Okay, so we can make a potential function based on how unbalanced the tree is. And in this way, when I do rebalance it, the unbalance goes back to 0 and it pays for the time spent to balance the tree. Okay, so that's good. That's great. Now let's again go back to the first thing. Okay, what happens if we don't rebalance anything at all? Now we pay log n time just in real work to insert the key. And then the potentials also all go up by potentially a little bit, right? Because things might get unbalanced. So I need to argue that this is all at most log n. So maybe one way is as I go down, each tree, how much can its potential go up? Some particular x. So I've inserted a key down below, and I'm looking at this particular node's potential function. How much might that potential have increased by? 2, or I guess 1 was what I had in mind, but because you inserted one node? Okay. All right, so one tree's potential function may go up by 1. You might get lucky, it might go down by 1, but we're just doing worst case, right? So for each tree along, subtree along the way, the potential goes up by 1 at most. And then how many subtrees are there? Log n, I think I heard. Log n because the height is always at most log n. Because it's also already mostly balanced everywhere. Okay, so log n trees, each of those potentials go up by 1. So you pay log n in the increase in potential. And then if you do have to rebalance any of those trees, the decrease in potential will pay for it. Okay, so yeah. Earlier you said, why do we need a potential function? And then you suggested a potential. Okay, so that would be an example of using a potential function to argue that lazy rebuilding works. Okay. All right. Good. Any questions? This is a pretty easy data structure to implement. Oh, it might take a little time to do the rebalancing part, but if you're comfortable with amortized analysis, I think it's very easy to see why this is correct. It's difficult insofar as amortized analysis is like a brand new thing that you learned about half an hour ago. Okay. All right. Now, this is even better. All right, how do you do deletions, right? Deletions are a huge nightmare for binary search trees, right? Because you go through and you find the key that you want to delete. If it's a leaf, great, because you can just remove it. But if it's stuck in the middle, right, now you're in a world of hurt because you need to like replace it. So you can like go find the next key that comes right after that's like hopefully a leaf and put it back up. But it might not be a leaf and you have to like keep doing all this crazy stuff, right? So deleting from a binary search tree, especially if it's some intermediate node, is like a huge pain. I don't quite remember how AVO trees and red-black trees dealt with it. Do you guys remember? Okay, so no one remembers. So that's the point I'm trying to make here. Okay, so it's a real pain to delete because you're taking things out of the middle, and that all those nodes play such an important role in the structure of the tree that just removing something is not so easy, right? Okay. All right, so I'm going to try to come up with the laziest way to deal with this. What is the laziest way? Yeah. Oh. As for all the subtrees that. Oh, okay, that is kind of lazy. So, okay, I find that X, and then I rebuild that whole tree starting at that X. Okay, my one regret there is that it will take a while. I mean, it takes linear time to delete, right? So, like for example, imagine I was always deleting the root of the tree. Then every time I'm paying, linear time. So I want to do something that's actually going to kind of take more like constant time. Well, log in to find the key, but then otherwise not much effort. Um, but again, it's much easier than like having to repair the tree. Yeah. So the rightmost child in the left subtree. But what if that's not a leaf? That's also in the middle. Oh yeah. Okay. So you can do this thing where yes, that is true. Uh, that is true. No, it doesn't have to be a leaf, right? Like, well, okay, so you can keep doing this recursion thing, right? So you can go and then you find the rightmost, but okay, but it might not be the rightmost might not be a leaf. So then you say, oh, now I have to also figure out how to replace this guy. And you have to recurse and recurse. Well, okay, so in that example, the rightmost might still have left children, right? So it's not a leaf. But you could like recurse and keep going and try to keep replacing, but it is somewhat involved because you have to keep bubbling down. So I'm looking for something easier. Yeah. Oh, sure, sure. Okay, so let me make this. Okay. So let's say it looks exactly like this. So that's the key you want to delete. And then you have one node to the left, one node to the right. And then down here, you have a nice big complicated subtree. So this is the rightmost. You remove the whole right. So, okay. Sorry. This is this, and you have another subtree here. Okay, so you find this guy. This is the rightmost in the left subtree. And you can't if you just put him up here. Oh, okay. So you can do more work like this. Okay, you can put that there, but you still have to fill that hole. No, I mean, stuff like this is doable. I mean, people, the other data structures do this stuff, but there is some kind of bubbling down and recursioning. Anyway, what I'm trying to get at is obviously going to be much simpler. Yeah. Okay, perfect. So we won't really delete. I'll like mark it for deletion. I'll say, I'll just put like a Boolean flag there and say this node got deleted, but I'll still remember the key there. I'll leave the key there so you can still go left, right, left, right, left, right. Okay, so I'll just mark it for deletion, and I won't worry about like rebuilding the whole tree and trying to figure out the leftmost, rightmost child of, aunts and nieces and all that. Okay. So, okay, and the only liability is that if you delete a lot of nodes, a lot of things are getting marked for deletion, and now you're starting to waste space, right? Maybe you deleted 99% of the nodes, and they're all sitting there in memory. So we'll basically add garbage collection. If at least half the nodes in the tree get marked, then I'll rebuild the whole thing optimally. That'll take linear time, right? So just lazy deletion. I'll just mark it for deletion, wait for enough deletions to accumulate, and then I'll just clean everything up and rebuild the whole tree in linear time in the remaining elements. All right. How can I justify that this takes a really, log n amortized time? Yeah. Oh, yeah, that's nice and easy. Yeah. All right, so let's define potential to be number of nodes marked for deletion. Okay. Then, you pay log n time to find where the thing is. Then you mark it, so you spent log n real time. And then your potential went up by 1. So it's log n. And if you have to rebuild it, right, and if there's like n nodes left and n are marked for deletion, then you spend, your potential was size n, and you need to spend roughly big O of n time to rebuild the tree. So, yeah, so potential function is great. If you could come up with a nice, concise sentence, then it just captures everything for you. Okay, one thing I'll mention is that to do it all correctly, you want to combine your potential for deletion with the potential from previous, because you want to say that insertion and deletion both take log n simultaneously, but that's not so hard to do. You can use still the same potential function, argue that everything's okay. Okay, all right, so those are very lazy binary search trees that get you log n amortized time for both operations. The point being is that you could probably remember all the algorithmic details of this approach, whereas I don't remember red-black trees. Okay. The relative simplicity, I mean, it's all big O of log n, but they're all relatively simple algorithms, and that leads to good practical performance as well. I mean, the ones today. Okay. All right. All right. This is our last set of examples. I think we barely have enough time. All right. Does anyone here like to mess around with weird languages like Haskell or Lisp or? Okay. I love Lisp. Anyway, so these functional programming languages are often based on something called immutability. Okay, which is a really simple rule. It says when something gets written down, you can never change it again. Like once it's written in memory, you can never rewrite that same spot in memory. Okay. That seems like a very strict rule, but it's really nice. Well, first you do it like kind of for like in the programming language world, kind of like theoretical reasons. But one thing really nice is like if I know that my data will never change, my x, then and I give it to some function f, right? And I compute f of x. I know that f cannot mess with my data. right? So I can keep using X, knowing that F can't screw with it because no one is allowed to change X once it's written. Okay, so that's really nice. This is especially useful if you're doing like parallel programming and concurrent programming and stuff like that, where you have things flying around everywhere. And if you don't have a rule like that in place, it's like impossible to keep track of all the side effects and stuff like that because you have different parts of the CPU. I mean, different threads changing the same memory and it's just chaos, right? You can use like an infinite number of locks and stuff and then you just hate yourself. Okay. Um, Also, having this kind of like strong rule makes, lets your compiler have stronger assumptions, right? Because it knows certain things won't change, and then it can streamline some things. Okay, but obviously this is also very restrictive, right? I mean, if you write something, you can never rewrite, right? So, okay, well, maybe I'll mention like a really simple example of an immutable data structure that's really important. For example, in Lisp, it's just a linked list, right? So a linked list will have these nodes that sort of just have two fields. One goes to the data, or in Lisp it's called the car, and the other goes to the next node in the list, okay, and sometimes called the Kadur, right? So this way you can make a huge string of data, okay? Now, if I wanted to prepend something to the beginning of the list immutably, how would I do that? So everything that's written, I can't rewrite, right? So everything in blue right now is frozen. But if I wanted to add a new element, what I would do is I would add something to the beginning with some new data, and it would point to the next one. And then I'll hold on to a pointer to the new head of the list. Okay? But the point is that I've prepended to the list, and I haven't changed any existing thing. Everything that was written was already written. If some other part of my code is looking at a suffix of the list, nothing has changed from their point of view. Okay? Likewise, if I wanted to remove the first element from the list, I don't like actually go in and deliberately delete it or anything. I just change my pointer from the head of the list to the next one. Right? And if somebody else was still using the beginning of the list, so be it. Okay, so a linked list is sort of the standard thing. Yeah, that's right. So there's some things you can't do, but you can do a linked list. Yeah, so we'll keep going, just in the interest of, okay, especially in the interest of time. I'll only mention one thing. So one situation where this might be painful is you imagine having like object-oriented programming and big objects with lots of fields or something like that. And now when you want to change one field, you have to actually copy the whole object and just replace the one field. That might seem really bad, right? Especially for a really big object. But often in real world systems, you have one object that has a few pointers to some more objects and a few pointers to more objects and stuff like that. And if I want to take my original object and make a new one with just one field changed, okay, and I'm worried about all these pointers, I don't have to copy all these things over. I make a new copy and I just copy those top pointers and I change whatever field I need to change. Okay, so when I'm copying like a deep object with lots of pointers to each other, I only have to copy really the top one. And the other ones, they just get the same pointers. Okay. All right, let me get to the point though. All right, we're going to talk about how to implement stacks and queues immutably. Okay, stacks are pretty straightforward. How would you implement a stack immutably? Yeah, a stack is just a linked list, right? We add to the front, we take off from the front. So actually, we already know how to do a stack. So that's easy to do a stack immutably. So here's the fun one. How do you do a queue immutably? This is tricky, right? Because I want to insert at the top and delete from the bottom. You can't just delete the last one, right? Okay, so you want me to, so you roughly want to take the stack one, but how do I delete this, right? This pointer This green pointer, I can't change this. So I can't erase anything. I can't change anything that's already written. Let me phrase the question a little differently. Can you implement a queue using only stacks? Okay, how? Okay, we're going to make two stacks, one for things coming in and one for things going out. So those two stacks will combined contain all the elements. Okay, so I have a stack on the left. Every time I'm inserting elements, I'll put it from there. Stack on the right, every time I'm removing elements, I remove it from the top, right? So the order of the stack, order of the queue looks something like this from beginning to end. Okay. Now, what happens, what should I do once I've emptied the entire out stack, right? And I want to pop another one, right? I want to remove another one from the queue, but the out stack is empty. What would I do? Yeah, or I can take this and I can like flip it all over. Okay, so if I have something like this, the elements are listed A, B, C, D, E, F, and then I'll just flip them all over into the out stack. Okay. All right. All right. Anyone want to try to argue why insertion and deletion would take constant amortized time? In particular, the only thing I have to worry about is justifying the big flip. And then we're done and you're out of here. Yeah. Yeah. Yes. That's true. That's true. So yeah, okay. I 100% agree. I just want to sharpen this a little bit so I can really formally say it takes constant amortized time. So if we can come up with like a nice credit scheme or a potential function that can pay for moving everything over. Because that operation does, when I flip everything over, if there's n elements, it does take n time. So I just want to kind of charge that off and then we can all go home. So any credit scheme or potential function to pay for moving everything over. Yeah. Okay, yeah. So for every insertion, I can imagine also putting a dollar on, say, the element who got inserted. Okay. And now when I flip everything over, there's as many dollars as there is elements, and that's how long it takes to flip everything over, and so that'll pay for that operation. Otherwise, when you have the stacks there, pushing and removing takes constant time. Okay, so then you get two stacks make a queue with constant amortized time. All right, that's all I had, and so next time we'll do a little bit of randomized stuff. All right, thanks guys. Sorry for going over.